Yep, so this lecture is about estimating hyperbolic discounting models, but in almost every lecture that I attended, there seems to be a question about identification of discount factors or how the discount factors are estimated. So I think with this topic, it will not only cover hyperbolic discounting models, but also the results would apply to geometric discounting models as a special case. So here's a roadmap. So in this summer school lecture, I'll provide an introduction of hyperbolic discounting models, assuming some prior knowledge of dynamic programming techniques, which have already been covered in previous lectures. And consistent with the DSE theme, I'll focus on the econometric underpinnings of these models, which actually is an open area for research. And then I'll discuss some empirical applications. And this is a very old topic. I think the very first papers appeared 50 years ago, at least. And it's a very general topic that spans several fields in macro and microeconomics, and in both theoretical and empirical economics. And they all have very, very different focal points. But in today's lecture, I'm going to be a bit more specific. So my approach would be to focus on the econometrics. Although the historical motivation for these types of models are often behavioral. And I must confess that my knowledge in this area is limited, and it's been a while since I've worked on these models, and I hope that the econometric focus will provide a more useful perspective in this broad area. So some examples would include like consumption saving models or addiction. And if you just Google search hyperbolic discounting, you see all sorts of references pointing to these different areas. I'll heavily draw on recent papers, which I find to be more exciting. So I tend to move on to various different topics that excites me, and perhaps you feel the same. And these recent papers cover formal identification and estimation of such models in a dynamic discrete choice setting. So a lot of the time we spend on discussing the specific details of the paper by Bring, Dalio, and Ishkakov, 2019. And identifying present bias discount functions in dynamic discrete choice models. If time allows, I'll also talk a bit about a paper released earlier this year by Wang, Wargreiber, and Xiao. With these sorts of models involving terminating action. And the backward recursion in these papers have similarities in algorithm and also in terms of notation. So they fit together in one lecture in a pretty convenient manner. And after I talk about the identification approaches, I'll discuss a pretty recent empirical application and in relation to the practical considerations and also the econometric issues involved in the empirical setting. So that's the approach that's taken today. Before I move on to discounting, I just want to have a slide describing what's the overall issue facing a modeler in relation to building dynamic structural models. So dynamic structural models, they take a stance on what agents are maximizing and what are their information sets. A modeler ponders upon the following difficult issues. And I don't think a thorough solution has been developed yet for each of these issues, let alone a combination of these issues. So how do agents compare the present with the future? What information do they act on? What are their beliefs? Are these constructs stable over time? Is the model correctly specified? I'm often terrified by mystification of models, so there will be some slides saying that the model might be too tightly specified in relation to the data. And are there simpler models that can do the same job? So this is very, very vague. So the job can be described in relation to the sort of counterfactual policy experiments that you'd like to explore. So if you want a wider set of counterfactual policy, if you want the model to be more powerful, you're likely to impose more explicit assumptions to the model so that they can give you predictions in a wider set of counterfactual settings. But I think maybe conceptually there's a frontier at which you can simplify the model as much as possible, given a vague set of jobs that you'd like to achieve. Okay, now understanding the dynamics of structural models, I think this is a more basic or maybe possibly fundamental question, existential issue, so to speak. Geometric discounting, which is based on time-separable preferences, forms the backbone of such models. But it might be potentially, I missed the word potential, potentially tightly specified. And policy counterfactuals, especially those that are time-dependent, will depend on this feature. I think these points have been partially reflected in your questions in previous lectures during the summer school. But perhaps when we're thinking about hyperbolic discounting models, it is useful to think of it as an avenue or a device through which we can develop better tools in the future to deal with these difficult issues that I listed above. So why do we need a dynamic model? So if it's a court case, the judge says, how do you set your discount factor? Is there a short answer? Is this best practice? So what's the best practice? So I think there needs to be a clean answer in order to be satisfying to the judge. So why do we need a dynamic model, and what's the empirical content of such models? So the content about hyperbolic discounting today will not thoroughly address these issues, but I think it is a good thing to just place these questions up front. Some technical details. So hyperbolic discounting factors envelope geometric discounting. So there are two discount factors. The first one is the present bias factor. The second one is just the normal discount factor, delta. And under time-separable preferences, we have UT, the utility flow, and a discounted sum of expected utilities in the future. And the first future period is discounted with a factor beta times delta, and all subsequent periods are discounted by a function of delta. So you get a drop initially, and then it slopes more gradually in all subsequent periods. In Abring, Delort, and Ishkakov, they derived conditions for identification of sophisticated quasi-hyperbolic time references in a finite horizon dynamic discrete choice model under a set of economically motivated exclusion restrictions. So a short answer to the identification of these discount factors would be exclusion restrictions. Those are the approaches that are more widely used nowadays. And the results about identification can be reduced to characterizing the zero set of two bivariate polynomial moment conditions. So the backward recursion procedure will result in some moment conditions that are highly nonlinear in these parameters. So so you don't get linearity, and that has implications for set identification. So the identified set is finite, but you don't usually get point identification. And their approach builds on the QE paper in 2009 for geometric discounting models, And a lot of the equations presented today would be generalizations of those results. So if we get through these results, we'll be able to also indirectly cover the huge literature on geometric discounting models. Now, I jump back and forth, so I jump to the econometrics a bit, and now let's talk a little bit about the behavioral motivation. The historical motivation for hyperbolic discounting models has been motivated by evidence of preference reversals. So in this classical Thaler-Apple example, you'll be presented with several scenarios. Subjects who prefer 1 apple today to 2 apples tomorrow would tend to prefer 2 apples in 1 year and 1 day from now, as opposed to 1 apple 1 year from now. So you make some comparisons at different pairs of points in time. If you can observe evidence of reversals, that will be interpreted as direct evidence for hyperbolic discounting behavior. And these have been considered as the defining feature of time inconsistent preferences, and they have been considered as the core of an identification strategy. But I mentioned just at the beginning that the literature evolved from widely different perspectives, theoretical, empirical, and very different focal points. So this is a focal point from behavioral implications. And but historical motivation aside, if we consider geometric discounting as a potentially tightly specified model, it's natural to think about the possibility of relaxing this model without losing its empirical content. So as I said before, we'll just focus on econometrics and then some empirical applications. We'll talk about the behavioral preference reversals a bit, but it's not the central theme of today's discussions. So primitives, so we have a standard setup for discrete choice dynamic models. Finite horizon, if I understand it correctly, infinite horizon problems is still yet to be solved. So I think the results are here for finite horizon only. We have action dt from the choice set big D, index from 1 to big K. Vectors of state variables are xt and errors epsilon t from epsilon 1 to epsilon big K. Observable states have finite support chi, assumed to have J elements, and they evolve as a controlled first order Markov process with transition distribution QK. So the subscript K indicates that choice K is chosen. So this is standard setup. The utility shocks epsilon K are assumed to be independent from the state variables, the prior states, the choices, independent over time, and cross choices, for simplicity, assumed to have a type 1 extreme value distribution, following a type 1 extreme value distribution. If agent chooses K in period T in state X, she collects a utility flow given by UK plus epsilon K, and we normalize the utility of choice big K to 0. Present bias time preferences are time inconsistent, and value functions do not follow from a standard dynamic program. And it is an intrapersonal game, as we just briefly mentioned at the beginning. We can think about the values as summarizing the payoffs to players in a Stackelberg-like game played between selves in different periods. Now, more notations. We denote sigma tilde t to be an arbitrary choice strategy, and boldface sigma delta, boldface sigma tilde t being a just a collection of sigma tilde t, the choice strategy, from the current period to the end of the time horizon to be a strategy profile. And the current choice specific value function for the non-terminal period is given by W. So here we have WK as a function of your state variable, and your strategy profile is from t equals to 1, being equal to your utility flow plus a hyperbolically discounted expected long-run continuation value, which I'll define in the next slide. And here the integral is taken over the state space. So QK is observed by us. X is observed. And in the terminal period, we have the terminal value WK to be equal to the utility flow. Now I take that equation to the top of the slide and then do a bit of arithmetic. The stream of all future utilities are discounted geometrically by delta. So remember what I said about the initial drop by beta delta, and then discounting in subsequent periods by delta. So here the V thing, which is core to the backward recursion procedure, is called the long run value function, which is discounted geometrically. So we see that WK here is initially hyperbolically discounted and then subsequently geometrically discounted. Now this function here, Vt plus 1, is again a function of your state and also your strategy profile defined at t equals t plus 1. It is expected sum consisting of the utility flow. The utility flow is determined by your strategy in t equals to 1, time period equals to t plus 1. So this is part of your strategy profile. So you know what to do given your realization of your state and also the error. And this is just the error, which is integrated out. And there's this forward iteration consisting of a geometrically discounted expected long-run value function, Vt plus 2. And in the terminal period, we have V big T equaling the expected utility flow plus the error. And here the future selves have strategies sigma tilde t plus 1. They all have present bias, which are in conflict with the current self's time-consistent long-run preferences. So that constitutes a game that is played by different cells across time. Some more terminologies. We call an agent sophisticated. So for this agent, her perceptions of the future strategies are correct in equilibrium, which means that a sophisticated agent correctly perceives her future selves are present bias. But there are other variants of these types of models where agents are considered as naive, which means that the current self thinks that her future selves are time consistent. So the belief is incorrect. But in those cases, you can still do the backward recursion and obtain these strategy profiles. You also have so-called partially naive individuals where the current self thinks that the future selves are present bias, but the present bias factor will be different from the actual present bias factor. So it's somewhere between a naive agent and a sophisticated agent. And in the intrapersonal equilibrium, her selves, all her different selves use a perception perfect strategy, which means that a strategy profile, sigma star, such that each strategy is the best response to the perceived future strategy profile. So, in this setting, you have the strategies to be defined recursively. So this sigma star at T would be just the argmax of something that is a function of your strategy profile from T plus 1. And by backward recursion from the terminal period, a perception perfect strategy exists and is unique. Now let's move on to the identification problem. It is done in a concentrated manner. So the first step would be to consider identification, assuming the discount factors are known. So what are the primitives of the model? We have the state transitions Q, we have the utility flows, and U big K is normalized to 0. And now let's, for the moment, assume that the discount factors are known. So we start with the CCPs. So the model gives us the CCPs. So the data gives us the CCPs. Defined here, you're all familiar with it. And we focus on the identification of, this is the ultimate goal. So we would like the discount factors to be identified along with the utility flows from the choice probabilities which are observed and the state transitions Q, which are all observed. So we start with this classical approach where we contrast the CCPs. And so we get this equation where on the left side, you have the contrast of the CCPs, and on the right-hand side, the contrast of the choice-specific value functions. And WU, as I discussed earlier, is given in terms of the hyperbolically discounted expected long-run value function. And this term is, you're all familiar with it, it's all over the place in the previous lectures. So these are just the log sum exponentials of the contrast of the choice-specific value functions. And this is observed. Now let's do the backward recursion. So by backward recursion, the utility flows are identified given the state transitions, given the CCPs, and given the discount factors. And to see this, observe the following. So you have the value contrast to be equal to the utility contrast plus the hyperbolically discounted expected long-run value function and integrated over this difference in the state transitions. And here, U big K is normalized to 0. And by the backward recursion procedure, VT plus 1 is known. And the state transitions are observed. And we can simplify this by combining some equations. So we have on the left-hand side, the contrast of the CCPs plus U small k, plus this hyperbolically discounting multiplicative factor multiplied by the differences in the state transitions times your long-run value function at t equals t plus 1. And here things, so it is, so the right-hand side is actually the same as the right-hand side here, except that we just rewrite some notations. So the Qs are the they're the row vectors that stacks the state transitions across X. And V is a column vector that stacks the long-run value function across X. So I move the equation up here and then go on to discuss the recursion. The core of the recursion procedure would be to express Vt plus 1 as a function of Vt plus 2. So the definition of the long-run value is just, as I said before, it's just the the utility flows plus errors plus this geometrically discounted long-run value at t plus 2 integrated over the error space at t plus 1. And here's the key step. So Vt plus 1 can be expressed alternatively as functions of the choice-specific value function and a correction term. And this is really the key departure from geometric discounting models. But before getting to specific, maybe let's plug in the geometric discounting setting where beta, the present bias factor, is equal to 1. And in this case, this correction term will disappear. And we will get the standard dynamic program. So this is just the Emax function. So how do we get this result? So this is a result from some combination of previous equations. And W, recall that it is given here with this hyperbolically discounted term. And what that equation did was that instead of having the discounting to be hyperbolic, you just correct it with this term here. So this term, if you just expand it, you see that it's just delta times this Q times V, which is part of your long-run value function, minus delta times beta times this same thing, which is basically canceling out what was being done in the W function. So we still have this this thing here, which needs to be simplified, and this is essentially just the functions of the Methenden surplus, which is written here as mt plus 1. Mt plus 1 is just the Emax, which, as I mentioned before, can be computed by pure features of the data. So we get this surplus plus the choice-specific value at the reference choice big K, plus the correction term. And we also have W big K to be equal to beta times delta times Q times V t plus 2. And here we get this because the reference choice, the utility of the reference choice is 0. And we also get this term, this expected value can be just written as a weighted sum where the weights are the CCPs. And with all these equations, we yield a simple equation given here, which is expressed as a recursion. So Vt plus 1 is equal to your the Methenden surplus times delta bracket a mixture. So if beta is equal to 1, we don't have this term. And this is equal to 1. So you get delta times big Q times Vt plus 2. So that's the standard dynamic program. But here, because the present bias factor is not equal to 1, you get a mixture consisting of Qk and Qt, Q bar t plus 1. And this is actually not trivial, and I'll define that in the next slide. But this is how the core of the recursion procedure is looking like. Q bar t equals to 1 is just a weighted sum consisting of the CCPs and the state transitions. It is the expected state transition probability distribution under the strategy sigma star t plus 1 in state X. And I think, again, the key message is that it's a mixture. And the mixture represents an expectation over how the choices of the present bias future selves control future state transitions. And these choices made by future selves are potentially in conflict with the current self's long-term preferences. We can further simplify the terms as follows. So instead of expressing this term as functions beta and 1 minus beta with these things, we can just write a simple, just define a simple term called Q, PB, T, beta, which is just this mixture. And it is a J by J matrix, J being the elements of the state space. So we'll be working with this term here from now on. And so so far we have assumed sophisticated agents. So you can see all this, the stars in the strategy profiles. Now we have condensed all these terms into something that's a bit cleaner. And this is a pure feature of the data. And here we have the discount factors to be in various places. So this outside, so this is just a multiplicative term. And beta, so this Q, this transition here is a function of beta only. And then we have this V plus 2, of course. And we can do the forward iteration, forward substitution. We get Vt plus 1 to be equal to Mt plus 1 plus a geometric sum consisting of the discount factor, delta, and some functions of the present bias factor, beta. And this is also obtained from the data. And combining this result with an earlier equation that connects the CCPs with these flows and values, we get this equation here. So of course, this is a data feature, and then you get the utility flow, and we get the hyperbolic discounting here, and we get the geometric discounting here, and some state transitions which are functions of the present bias factor. Now, so this is important, and the next approach, the next direction would be to construct exclusion restrictions that can cancel out the utility flows. So you then obtain a set of conditions which are nonlinear functions of beta and delta, and you solve them. The approach to exclusion restrictions have also been evolving over time. So as the papers are being developed, we move from higher level conditions to lower level conditions that are more interpretable by the modeler. So we'll just stick to that trend. So the intuition for an exclusion restriction typically delivers a variable that affects continuation values, but not the current period's utility. So we would like to perturb the future, the continuation values while keeping the utility flow fixed. And given pairs of these exclusion restrictions, you can just cancel out the utility flow accordingly. And such an excluded variable typically imply more than 2 exclusion restrictions of states, which further restricts the identified set of discount factors. I haven't really talked about the identified set, but just to project things in the future. So this is where we are getting at. And for simplicity, let there be 2 pairs of states, XA1, XA2, and XB1, XB2. And the exclusion restrictions indexed by A and B are given at a low-level form, which are in terms of utility flows. So you perturb the state, and the utility flow is the same. So that's an exclusion restriction. And you find another pair of state where the utility flows are the same. And in the empirical application, there will be such a example of this kind of exclusion restriction. So given the pairs of exclusion restrictions are available, we can just do some canceling, substitutions. So substitute this equation with your XA and XBs. On the left-hand side, you have the differences in the contrast of the CCPs. On the right-hand side, we have this term with the note that there's no longer any U's because the U's have been canceled out perfectly due to the exclusion restriction. And we only have beta delta times these differences in the state transitions plus this geometric term involving delta and beta. Do this for another pair of states, we get another condition here. And these are highly nonlinear in delta and beta. And the identified set is zero set of these two moment conditions. And we can perform estimation by, say, minimum distance or even OLS. Well, not in this case, but in some other cases, you can have OLS. Now, the identification hinges on some rank conditions because we need to invert things. So this is a function of the state transitions. So we need to assume this is non-zero. And for the other pairs of states, this is non-zero. And we also need some terminal conditions. So this is related to my earlier comment about finite horizon and infinite horizon models. So it appears that identification in infinite horizon models remain an open question. And given the rank conditions and the terminal conditions hold, the identified set is discrete with no more than the square of t, big T minus small t points. So that's the main result of the paper. Yep.
Can I understand the difference in differences? Is something like middle most like that? Is it something like differences?
Yes. Yes, it is. Yep. Yeah. So this is a scalar, and yeah. And we have just beta and delta. Now, enough econometrics. Let's move to lab approaches. So in lab approaches, we use contrast between observed choices for menus of sooner, smaller, and larger, later rewards. But here, so just in relation to the econometrics, which are new results, how do preference reversals enter into this? I think is less than obvious. It is definitely there, but so let's look at the terms again. So we have the long run value function equaling this geometric sum, where the Q's, the QPBs are mixtures. And this is the term that makes the hyperbolic discounting models differ from geometric discounting models. And this correction term broadly represents the expected preference reversals of future cells by the current cells. But if we just have observational data, if we don't have elicited belief data, then it is not immediately obvious how this term will exactly map into patterns of preference reversals, except that we know that in geometric discounting models, preference reversals are impossible. So here's an illustration with a 3-period model to show how the identified set would look like in such a simple setting. So we express these terms in deltas. So these are just differences in contrast of CCPs. And on the right, we have the I think it's differences in the transition probabilities, state transitions. And with some simplifications, we get this equation, which is conveniently expressed as linear combinations of these multiplicative discounting factors. So we have beta delta, we have beta square, delta square. So it is quite obvious that if we didn't have this term here, beta and delta are really not separately identified. But in this 3-period model, we also have this extra term here involving beta times delta square. So this nonlinear term will offer information to separately identify beta and delta. So it really hinges on some higher order interaction terms involving the discount factors. Alternative identification approach. So the Bring et al. Paper gave one approach, and I'm going to talk about an alternative approach, which is so they have different approaches slicing the distribution. So they complement each other in a very interesting way. So hyperbolic discounting models are undoubtedly more difficult to identify than geometric discounting models. And we need longer time periods. So of course, with only 2 time periods, obviously you just be able to identify one parameter, and we need longer periods to do it. And there are alternative ways to impose restrictions on the model for identification. And Wang, Graeber, and Xiao study identification for sophisticated and naive agents with, again, a finite horizon model. And I forgot to talk about the stationarity. So they assume stationary flow utility, whereas in the Bring et al. Approach, they don't assume stationarity in the utility function. And they assume a presence of a terminating action. So the source of exclusion restriction is quite different. And the way they cancel out the utility flows are different. But in this case, the hyperbolic discounting parameters are identified. And for sophisticated agents, we don't need to observe the final period. And in some special cases, linear so OS estimators are available. And I'll just give a very quick walkthrough of their approach. Start away by assuming stationary flow utility. So we write UKTX to be UKX. In addition, assume that the utility for the reference choice K, big K, to be non-zero. So basically, with a terminating action, your reference choice would yield this U big K, which is non-zero. They have to be estimated. They have to be identified. But once you choose big K, the model ends. There's no further value function iteration. So there's no continuation value involved after you choose the terminating action big K. In the baseline case, suppose we observe the final 3 periods of data denoted by the P's, P big T minus 1, and P big T minus 2. In the terminal period, we can write the value contrast as the differences in W which is equal to the differences in the U. In the second last period, we have differences in the U with respect to the terminating action K, plus this hyperbolically discounted expected long-run value function. So this Q times V we have seen numerous times in previous slides. And here it is, this VT is expressed as a function of P big T tilde. So that's your perceived. So there's still the intrapersonal game is still in at play. So the current self would assume the future selves follow some strategies. So that's why there's this tilde here. But because we're talking about the terminal period, so the perception would be equal to the observed observed P. So the model has been simplified, and we can just write the observed P as this familiar term, which is the negative log of PK plus UK. And the model primitives are beta, delta, and U big K. And recall that U big K is not 0, and it is to be identified. I may be a bit starting to become clunky here because I, instead of trying to lay out everything step by step, it involves some step jumping. So assuming the state transition matrix QK is full rank, so the notations they're consistent with before. We can invert this equation. Invert this equation here. As follows. So you can express U big K as the log of big KT. It's a pure feature of the data, plus 1 over beta delta times the inverse of the straight transition matrix, plus a pure feature of the data. And note that here, that this difference is made across time. So instead of imposing exclusion restrictions and canceling out the terms across the state, the exclusion variable, instead of doing this horizontally, instead of doing this vertically, you do this horizontally over time to cancel out the utility flows. So that's the big departure. And for a sophisticated agent in the second last period, we can just we can write the same thing mechanically as utility contrast plus this term here. And after some substitutions, you get this V big T minus 1 to be equal to this term here, involving your so this familiar term, negative log plus UK, plus some correction term involving delta and 1 minus beta. So this is the mixture thing that has appeared before. So despite the different ways of slicing the restrictions, you get this correction term involving delta times 1 minus beta. And again, when beta equals to 1, this correction term will disappear. Now, take the difference in log odds across time. So do this horizontally across time t minus 1 and t minus 2 to cancel out the flow utilities. We then obtain a system of big J equations with 2 unknowns, beta and delta. So instead of your earlier question, so instead of having 2 equations with 2 unknowns, you now have big J equations with 2 unknowns, and big J is the elements, number of elements in the state space X. So on the left-hand side, pure features of the data. This is observed. These are to be solved. Pure features of the data. These are to be solved. And you've got the Qs and features of the data. And then impose a rank condition. But so this is just one case where you observe the final 3 periods of data, and you can simplify the expression into a linear system. So the linear system has this form where you have the unknowns as collectively delta times beta and delta. And these are pure features of the data. So these are the elements that we obtain from this system of equations. And if we assume this omega has full column rank, then beta and delta are identified, and they can be estimated using OLS. So the identification has been shown through 2 different approaches with only observational data. And in this particular case, the last 3 periods of data, and can be done, the estimation process can be done using OLS. There are some other settings such as sophisticated agents and final periods not observed. And then instead of linear equations, you get nonlinear equations. So the parameters are only locally identified, and you need 4 consecutive periods of data. And the complication comes from the lack of the terminal period. So the terminal period gives you a lot of information on identifying the flow utilities. There are some results about naive agents, which I mentioned before, that which assumes that current self erroneously think that the future selves are time consistent. And the backward recursion is largely the same, but just a little bit different. I'll talk a bit about that when talking about the empirical application. Now, application, how much time do I have?
About half an hour, maybe 1 minute.
Okay, so I think I have enough time. Oh, yes.
So if you go to the previous slide, the 3 periods of data, 4 periods of data are sufficient for identification. Can we use more periods of data, and what happens in that case?
Over identification, which is a core feature in this empirical application, is severely over identified, I think. But you have, well, there's a case where you just do estimation by using the control group only, and then you can't really estimate the time preference parameters. I'll get to that point. Yeah, so this empirical application involves a policy called welfare time limits. But then I have to talk about preference reversal, because it's historical motivation. In practice, it's tricky to find direct evidence of preference reversal using standard observational data. And if you don't have the lab setting, it's pretty much impossible. And we have additional complications involving unobserved heterogeneity and selection. So so I won't go into much detail at this point about those things. Nevertheless, the identification results that we have seen so far rely on the nonlinearity of the backward recursion problem, and based on economically motivated restrictions. Of course, in the terminating action, you just impose the restriction based on the context, but they're all economically motivated. I'll talk briefly about my work in 2017, which estimates a hyperbolic discounting model of labor supply and welfare participation with heterogeneous time preference parameters. And in that case, the exclusion restrictions are constructed from time limits. There are variations in behavior induced by time limits in a welfare reform experiment. So the exclusion restriction will be in line with the ones described in the Ring et al. Paper. And here's where the identification becomes over the top. So actually, the model blends multiple sources of identification. So first, exclusion restrictions are captured via a variable that changes future continuation values, but not the utility flow. So that's already discussed earlier. The model assumes stationary flow utility, perhaps with good reason. Many periods of data. The last period is sometimes observed. So I briefly mentioned that the cases for identification will be different when the terminal period is observed versus when it's not. But here is you can assume it to be sometimes observed because the welfare time limit. If people exhaust the time limit, the problem becomes effectively static. So there's no dynamics anymore. There's a randomized control trial. Initially, I thought that it was just a quantitative extra feature that improved identification, but it seems to be more important than that because with a control group not subject to the policy, you don't have this exclusion variable anymore, and that gives you information to identify the utility flows. So these are not proven rigorously, but that's how the intuition goes. There's also the structure of the welfare program in nonlinear budget constraints that regulates work and welfare choice combinations. So this is another implicit source of identification that helps the modeler. The model specification is made to be reasonably flexible. Try to rule out the other different cases, possibilities that might be consistent with a hyperbolic discount. So you could have various different plausible explanations that compete with the hyperbolic discounting hypothesis. And it has unobserved heterogeneity. There's this technology in the wage equation, and also some because it's not a life cycle model. There's an initial conditions problem that needs to be resolved. And also different versions of the model are estimated and compared. So the empirical analysis has a lot of different practical challenges and considerations that need to be resolved. A geometric discounting model was estimated. Different versions of the hyperbolic discounting models were estimated. There were some model validation exercises. These are central to structural models. So for example, you could estimate the model on the treatment group who are subject to the time limit, and then perform validation using a control group sample. The paper showed that the other direction didn't work because in the control group, there's no exclusion variable. So there's no identification of the time preference parameters. So we actually try to estimate the betas and deltas, or even just the deltas, and with huge standard errors. So the empirical results confirm some of the theoretical econometric results earlier. I've done things in an inverted ways because the way the lecture was structured. So I started with the identification first. Now some empirical background and motivation. The paper examined the issue of welfare dependence, broadly or vaguely defined as the social welfare programs carrying perverse incentives that lead to dependence on the programs. So with welfare benefits, it can generate labor supply disincentives. Some people in the policy circle talk about the poverty trap due to reduction of earnings or income. Current participation in program may increase the probability of future participation, so that is state dependence. and time inconsistent preferences as one plausible mechanism for this. And under time inconsistency, there will be scope for so-called paternalistic policies. The reason is that when the present bias people make choices, they don't necessarily choose whatever is best for them in the long run. And so the benchmark would be evaluating the welfare via a long-run criterion, which is consistent with the long-run value function, the VT. Would be something that's central for evaluating whether these paternalistic policies are actually meaningful. And the program study was the AFDC TENIT program, which is a cash welfare program in the US for poor female heads of family with at least one child under the age of 18. There was a policy experiment called FTP, operated in Florida for between 1994 and 1999, which imposed a 24 or 36 month time limit on the treatment group. Now, again, an inverted approach to introducing an empirical paper. So welfare time limits, as I said before, was modeled as an exclusion restriction. So in this labor supply welfare participation model, we assume wage uncertainty and liquidity constraints. And the time limit works as follows. The person will become ineligible for welfare after the cumulative periods of welfare use, denoted by M, reaches the time limit. So it's not really where people think about the term time limit, they think about term limits or the different definitions, but this is how this is defined. So, for example, if you have a 24-month time limit, then you, if you participate, you add 1 month to your clock, and once you accumulate 24 months of welfare participation, you can no longer be eligible for welfare. So that 24 months, cumulative months of welfare participation can occur over a longer horizon because you can choose when to participate and when not to participate in welfare. The key intertemporal trade-off is that if you receive welfare now, you forego one potential future period of welfare use. And there's this option value or continuation value that creates an incentive to preserve welfare use for the future. To fix ideas, consider two otherwise identical individuals who have different values of M being the cumulative periods of welfare use. Now call them M1 and M2, where M1 is smaller than M2, and they have both not exhausted their time limits yet. Their utility flow is the same because they both haven't exhausted their time limits, but their choices, if they're forward-looking, could be different because one person is closer to reaching that M bar where they become ineligible for welfare thereafter versus the other person. So the choice patterns based on this variable M can reveal how the individual discounts the future. So that's the basic idea. And there will be no changes in behavior if people are not forward-looking. Summary statistics of control and treatment groups. So this is a randomized control trial, and actually I think Mathematica, the think tank carried out this, or some other think tank carried out this randomized control trial, and there is a policy report which you can download online just to see how people in practice in the policy circle think about these sorts of problems. But here, because the time limit is pretty tricky to model, there's scope for some research done by me. So here, the standard balancing table consisting of summary statistics of control group not subject to time limits and the treatment group subject to time limits. Differences by the minimal differences by demographic characteristics and by random assignment behavior. So if you look at total months of welfare receipt during the last 2 years prior to random assignment, there's not much difference between the treatment and control groups. So those seem to be okay in terms of the experimental design. So is it a taboo word here, but not necessary. Okay, so during the sample period after random assignment, we see differences in work patterns, welfare use patterns, and also combinations of work and welfare use patterns. But obviously, these are way too crude to say anything about what is the discount factor. Because I have talked about the exclusion variable a lot, so let's look at some work and welfare use patterns conditional on the exclusion variable M. So 11 periods of quarterly data. So this is the value of M, and plot the employment rates separately between the control and treatment groups. We see that for the control group, the employment rate doesn't really vary with the exclusion variable M. For the treatment group, you see that it increases by M. And we see a similar pattern, a reverse pattern for welfare. So for the control group, the welfare participation rate remains largely invariant by values of M. It declines by M in the treatment group. So this variation will be used for identifying forward-looking behavior. And you can break things down by work and welfare combinations by M. There are some interesting asymmetries. For example, if you consider people who do not work but on welfare, you see a big divergence by M. So a lot of non-work. So as M increases in the treatment group, there are less and less tendency to be a non-working welfare recipient. But these are working welfare recipients. And interestingly, they are pretty parallel over time. And I'll talk a little bit about the commitment problem in this welfare use setting. There's this work commitment problem where present bias agents undervalue the future value of human capital accumulation. There's also this welfare commitment problem where individuals may theoretically just be happy to take welfare to constrain the budget set of future selves. It is under contention, but it's theoretically possible. Another way to look at the data is by sample attrition transition rates. So so these are the states last period. So if I just crudely classify people by work and welfare combinations in the last period, what are their choices or choice combination patterns this period? And we can tabulate the transition rates separately by the control group and the treatment group. And these this notation says that the difference between the treatment and control group for that particular cell is significant at a 1% level. So it's just a two-sided t-test, very simple. And here we see that for the treatment group, the transition rates are pretty different than the ones in the control group. And if you consider, for example, people who were non-working welfare recipients in the last period, if they're in the treatment group, they are much less likely to remain in the same state compared with a similar person in the control group. Oh, but by the way, these are just pooled observations in the data, so they're potentially endogenous. But you can tell that the experiment made a difference. For people who were working welfare recipients in the last period, you see that if they are in the control treatment group, they are much more likely to remain in the same state relative to an individual in a control group. And just a brief remark about the welfare program structure. So the marginal tax rate is, or the benefit reduction rate is very high. So if you do not work and you take welfare, you get the full welfare benefit amount. If you work a little bit and you go on welfare, your welfare benefit is deducted against your income. So you could have cases where, technically speaking, a person could work part-time and then just get $20 in welfare benefits per month if he or she wants to participate in welfare. There's some interesting patterns in here that might not be really consistent with a geometric discounting model. Okay, so the model, 3 levels of labor supply, whether to participate in welfare, some state dependence preferences, as experience accumulation. We can study the work commitment problem as in found in Silverman 2004. The model also has to deal with the initial conditions problem because the initial experience at the start is measured at the start of the random assignment. And if there's unobserved heterogeneity, then you can't just set the experience at the start of random assignment at a fixed value or 0. The model will be specified. So as in a dynamic panel setting, we need to deal with the initial conditions problem with regard to experience. Unobserved heterogeneity, there are 2 by 2, that's 4 unobserved types of individuals. So there are ability types. So high ability people would get higher wage offers. And 2 preference types. The preference types reflect preferences in the utility functions. And so those are the utility flow preferences and time preference parameters. But normally you would, if there are not a lot of dimensions of unobserved heterogeneity, just integrate it out with a vector. But here they are that's related to implementation. To make the model a bit more flexible, the ability and preference types are correlated via some equations in the appendix. And the probability of each type of individual depends on some initial conditions. So for each individual, you can actually compute the probability of each type, and the types determine the preference parameters. So in the end, you get in the population, each individual would get a different sort of predicted value of the time preference. So you can actually map out the distribution of the time preference parameters in that sample, which has more than say 16 points of support. It can have hundreds of points of support. And in terms of the preference parameters, they are heterogeneous in observed and unobserved ways. These estimates determine the self-control problem and commitment problems. I've mentioned this a little bit earlier. And people may choose a commitment device that allow them to restrict their future budget sets. So there'll be counterfactual policies that are shown in the towards the end of this lecture that show that if we impose a sanction regime, would people prefer a sanction regime over no sanction regime? So for time consistent people, no one would choose a sanction regime over a no sanction regime. But for present biased, potentially present biased individuals, they might prefer a sanction regime. depending on how the sanction is being designed. And the estimated model will figure out, it will compute the proportion of the sample that prefers sanction regime over no sanctions. And the policies are evaluated using the long-run criterion, which is just the long-run expected value function. And this is how the backward recursion was done, which is just basically similar to the slides about the identification. So recall the continuation long-run value function given an arbitrary continuation strategy profile, kappa, plus this is just the strategy from period T up to the terminal period. It is discounted geometrically. So delta here is not a constant. It differs by I, individual I. And Q is the permanent unobserved heterogeneity that needs to be integrated out. I won't talk about the implementation, just to briefly touch on that. And for a perceived continuation strategy profile, kappa tilde plus, which is just a set consisting of the strategies in each period from the current period to the last terminal period. The strategy in period A is a function of naivety factor beta tilde. So I talked about partial naivety. So in the sophisticated agent problem, this will just be equal to the actual present bias factor. So you do the backward recursion, assuming beta tilde is the actual beta. For naive individuals, this is said to be 1. So the current self thinks that the future selves are time consistent. They think that the future selves have present bias factor equal to 1. And so the backward recursion assumes by induction that EA VIA plus 1 is known. And then it solves the strategy at period A. Okay, so I think this is cleaner. So start from this expected long run value function, which is a function of this kappa tilde plus T plus 1. Solve for kappa tilde at period T. And then you then have this long run value function at period T, which is a function of this thing. This is just this in combination with this. And note that as a byproduct, we can write the perceived choice-specific value function. In previous slide was W, but it's the same here. So this thing is just equal to the utility flow plus the hyperbolically discounted expected long-run value function. And we can then form the perceived choice probabilities as a logit. So the P's are computed. And then we complete the backward recursion by taking expectation of VIT at period T minus 1. So so this is the Buffet surplus, and so we have already seen all of that. So, but what's common is that there is this correction term with delta and 1 minus beta, and these things are, I think, we've already seen them from before. So this is just a weighted sum consisting of the choice probabilities. And basically, in practice, you just do the backward recursion and impose a correction to keep the long-run value function in place, expected long-run value function in place at each period, starting from the terminal period. And so that's how the recursion is done. And for individuals who make So we've done the backward recursion, now the estimation. So when an individual makes actual decisions, she believes that her future selves will follow the perceived continuation strategy profile. And the current self's optimal strategy, I can write it as kappa star IT, which is not used in backward recursion because the actual present bias factor is not necessarily the same as the perceived present bias factor. So here, instead of beta tilde delta, you get beta times delta. And this is used in the likelihood estimation. So, yeah. And model parameters, so these are, I won't go into details, but I just want to point out that the discount factor will differ by demographic characteristics as well as this type specific intercept. And the same for the present bias factor and the naivety factor. And there is work preferences, welfare preferences, and some combination of preferences differ by demographic characteristics as well as by the type specific intercepts. The log wage equation is determined by your experience, and there's this curvature in utility. So just to allow for risk attitude or income effects, allow this curvature to differ by demographic characteristics. And then the shocks to utility and the shocks to the wage, they are also heterogeneous. So everything is heterogeneous, and the type probabilities are endogenous because of this initial conditions problem. So there's some random assignment characteristics that determine the ability type and the preference type, and the ability type and the preference type can be correlated. And I think that I remember that they're possibly correlated. And so all these are so estimated. And if we estimate a time consistent heterogeneous discount factor model, we get the discount factor with a mean of 0.73, standard deviation 0.07. And these three graphs show the baseline model, which is a heterogeneous hyperbolic discounting model. So this is the discount factor distribution, the present bias factor distribution, and the naivety factor distribution. So this is all over the place, even exceeding 1 for some individuals. So I just took a snapshot of the paper, and there's a paragraph that tries to explain what's really going on. So around 1/3 of the individuals have a naivety factor exceeding 1. It seems ridiculous, but when I think about how the things are discounted, you need to look at the aggregate discount factors, which is beta delta square, beta delta cube, and so on. So with a naivety factor exceeding 1, you actually have the perceived aggregate discount factor to be beta tilde times delta, and delta is less than 1 for these individuals. So when you multiply them, you get 1 and 1.01. So in fact, for the perceived discounting is actually flat for the first 2 periods and then declines afterwards. And the actual aggregate discount factors would follow just a steep decline followed by gradual decline for subsequent periods. We also have some. So the main message is that people generally can perceive themselves as time inconsistent. So they may adopt a commitment device, and around 1/6 of the individuals have perceived their future selves are almost myopic, which means that they think that the future selves are just dumb people. And goodness of fit by exclusion variable. So these are predictions minus actual outcomes by the value of M, the exclusion variable. So the baseline model gives this deviation of fit, whereas for the time consistent homogeneous discount factor model, which is the benchmark model in most of the literature, would give a rather different kind of fit. So it's an improvement of fit, and that's also compared using likelihood ratio tests. You can, so one model encompassing another and just compare the likelihoods, and they are in support of the heterogeneous present bias model. Now, some last remarks about counterfactual policies. So are there policies that are specifically related to commitment device or self-control or present bias problems? So there's this counterfactual where you give a payment to people who do not work and do not receive welfare. So for people who are really idle, pay them $50 per month. And in time-consistent models, everyone would prefer this policy regime because it makes, I'm not talking about general equilibrium, but just a partial equilibrium approach. Everyone would prefer that, but in this baseline model, only 90% would prefer this regime. And I've run out of time. Okay, so a couple of minutes. Okay, so so imposing dynamic sanctions or income support. So start with a basic scenario with the income support, and then try to impose some sanction regimes, but specifically to try to leverage on the commitment problem by individuals. So there is one particular sanction regime where about 1/5 of the individuals in the sample would prefer a sanction over no sanctions. And if you make things revenue neutral, actually 70% of the sample would prefer this kind of sanction. I'll just leave the details to the paper. And for a time-consistent model, as expected, imposing a sanction, no one would just would prefer this regime. So 0%. Okay, so are there some extra results by heterogeneity? So you get the baseline model with different people with different discount factors, and then you just group them, and then just to see whether people who are more present biased would have a higher proportion of preferring the sanction regime over no sanctions. Okay, so I'll stop here.
Thank you very much. Are there any questions? Yes.
Yep.
Add to the first part, which is you said a few times that that's the knowledge loads for the stationary analyzing tools. I think that's right for the 2019 version side. The version 1 year later, the main problem, you don't see it a lot because you can provide sophisticated agents basically solve an infinitizing game, and it's certainly complicated, especially resistance model. And I guess the literature suggests that in general we need developing strategies and solve it. Messy, so there's not much out there. But it turns out that we need the metric specification where we have this logic charts. The logic charts that affect the future themselves. Actions actually serve as privately observed charts that allow it for more strategies. So we actually show that resistance of an hyperbolic case, otherwise the unification strategy is basically the same as the backwards.
I see.
I just want to know that you're talking very good at actually still the paper.
It seems that the paper, but I had trouble downloading the 2020 version of the paper. It just has a cover page. So
Okay.
the only latest version that I got was the one here. Can you send me the paper?
All right, well, thank you so much.
Thank you.